In GR, gravity is described as the curvature of spacetime. GR is presently the best experimentally supported theory of gravity. It is responsible for incredible predictions, including both black holes and gravitational waves. We're therefore very interested in finding solutions to the equations of GR, which we call the Einstein equations. But these equations are very complicated. Because of this, there are many interesting scenarios for which we can't explicitly write down solutions, but instead have to solve them approximately using numerical methods. In fact, the Einstein equations are so complicated that we need to use supercomputers to do so. The science of solving the Einstein equations computationally is called numerical relativity. Gravitational waves are ripples in spacetime curvature that propagate at the speed of light. They are produced by the acceleration of massive objects, but are incredibly weak and so hard to detect. Because gravitational waves are so weak, the only sources that we can actually see involve large compact objects, like astrophysical black holes, which collide with each other. And even then, to actually detect signals, accurate numerical calculations of the waves are required. One important scenario to handle computationally is therefore the in-spiral and merger of two compact objects. The basic picture here is that as the two objects orbit each other, they emit gravitational waves and thus spiral towards each other, with the waves travelling out to infinity. Actually, much can already be done, but an open problem that I find fascinating is to calculate the waves all of the way out to infinity from first principles. Since computers have finite memory, you'd naively think that it would be impossible to include infinity in the computational domain. But it turns out that by carefully choosing compactified coordinates adapted to outgoing waves, it is possible to do so. Because they draw infinity to a finite coordinate distance, this choice necessarily introduces large numbers into the problem. But there is also a smallness coming from the fact that as we head away from the two black holes, the gravitational field falls off. Understanding the rate of decay quantitatively is a problem in its own right that depends upon the formulation of the Einstein equations that we choose to solve. Different groups of researchers have different strategies, but whatever path is taken, what's fascinating is that the smallness and the largeness compete with each other and can be offset so that in the end you can build a set of equations that can actually be solved numerically.
If you enjoyed the video, like and subscribe. And don't forget, you ask CENTRAnswers.